Moving on to chapter 5, we're going to talk about molecules and compounds and go quite a bit into naming. I always think of Juliet Capulet. What's in a name, right? Of course, she was talking about Romeo, but not about two star-crossed lovers this time. It's more about our system of naming, and we have a very exact system of naming in chemistry. So we'll go over that among other things in this chapter. So one thing about molecules is the properties are vastly different than the elements. So remember when I talked about the alphabet, like almost like every letter is like an element, and then when you join the letters together to form words, words are sort of like the compounds, and then the compounds we use to describe the entire universe. So except instead of 26 letters in the English alphabet, we have 118 elements to describe the cosmos. So it's a bit more interesting. So table sugar, so the stuff you get from beets or sugar cane, that is a molecule called sucrose. And it is a molecule, it's a stable group of atoms. It has carbon, hydrogen, and oxygen. And the properties of sucrose are very different than plain old carbon, whether it be graphite or diamond, hydrogen, which is typically a gas at this temperature and pressure, and oxygen also, diatomic molecule, sort of like hydrogen. So sucrose is very different than all those elements, and it has its own properties. So let's look at another example. Sodium. Sodium is a very reactive metal, and chlorine is a very reactive gas. Both of these are very, very poisonous. They're very reactive, and they can do you quite a bit of harm. But sodium chloride, so you react sodium metal and chlorine gas, form sodium chloride, and this is table salt. This is the most common salt that we have, and it's a completely different property than sodium and chlorine. So we have a whole new, this compound is very different. So most of the things we encounter everyday life, they are not elements. They tend to be, at least the pure substances, they are almost all compounds. We do see a few elements in nature. Oxygen and nitrogen in the atmosphere, gold we can find in its pure form, sometimes silver, sometimes platinum, sometimes sulfur. But typically speaking, we usually see things compounds. Compound is different than a mixture. A mixture is a bunch of pure substances, where a compound is a specific substance. Also, compounds follow the law of definite proportions, means that the number of elements that make a compound are set. So, and for mixtures, the number of pure substances in them varies. So look at this mixture. The mixture of a hydrogen and oxygen gas. So this does not necessarily have a constant composition. I mean, you can have various concentrations, and they can change. So another example of a mixture, if you want something a little more tangible, at least for those of us that live around the ocean, is seawater. Seawater is relatively consistent. It's typically about 3.5% salts, mostly sodium chloride, but that's different than the ocean water that's in the San Francisco Bay, where it's brackish and the concentration is less than 3.5%. So that's another example. The ocean water is an example of something that is not a consistent mixture. It also changes day by day as well. So chemical compounds, so for instance, compounds have set elemental ratios. So the composition of a compound does not change. So for this, Joseph Proust is the one that had this idea. The law of constant composition has to do with the same proportions of the elements. And for instance, for water, and this is by mass, I mean, they were working by mass. We're going to work by atom or by mole in this class in general, but by mass, the ratio of oxygen to hydrogen is 8:1. And this is true for all water. Same thing for ammonia. Ammonia, and again, looking at mass, for ammonia, the ratio is going to be 4.7 mass grams of nitrogen to 1 part mass of hydrogen. So atoms, when we talk about atomics theory and when it comes to compounds, there's going to be whole number ratios. But for mass, they do not necessarily have to be whole numbers. So when we have a chemical formula, it tells us the number of whole atoms in the ratio. So H2O, for instance, H2O is a formula for water. It means there's 2 elements of hydrogen to 1 element of oxygen. I mean, of course, a single molecule is going to be an atom. And that subscript there, the 2 and the hydrogen, indicates there's 2 of those hydrogens. The 1 is dropped. So if there's 1, you do not indicate the 1 subscript. So the 1 in oxygen is omitted. So to show you again here, so H is a symbol for hydrogen. The subscript 2 indicates there's 2 of them. O is the symbol for oxygen, and the lack of anything implies it's 1. And chemical formulas, we can see this. So sodium chloride means a 1-to-1 ratio. And then carbon dioxide, that means there's going to be 1 carbon to 2 oxygens. So this formula is telling us what the ratio is of the elements. And here's sucrose. The sucrose means there's 12 carbons to 22 hydrogens to 11 oxygens. So this is one thing to note, and you can look at sucrose. Sucrose is also known as a carbohydrate. Sugars are known as a classification of carbohydrates. And it looks like there's 12 carbons to 11 waters, if you follow that. Carbohydrates are not true hydrates of carbon, but the chemistry name, a simplification for that, has stuck. So if you wonder where the word carbohydrate comes from, it's from that. But the molecule is not a hydrate of carbon like carbohydrate would suggest. It's actually a much more connected molecule. So let's look at these 2. We have carbon monoxide on the left and carbon dioxide on the right. So carbon monoxide is toxic. It will kill animals, including us humans. And carbon dioxide is well, we need it, and so do plants. Plants use it as a food source, and we humans use it to regulate our blood's pH. So carbon dioxide is very important. So just the addition of 1 atom can completely change the properties of the molecules. So CO2 is carbon dioxide. I mentioned this. It's an important molecule. So when we name elements, you list the metallic elements first. So for instance, for salt, we call it sodium chloride. We don't call it chlorine sodium. I mean, I don't even know how I would name that, because it's just there's no convention in chemistry. So the ones that do if the molecules have nonmetals only, you put the more metallic-like element listed first. And that means it's the furthest to the left and the furthest up in the periodic table. So that's the way you would name it. And well, here's some of this is the table showing that. You can also think of it as the more electronegative, the less electronegative atom goes first. There's a few exceptions. So we say OH minus for hydroxide. We don't put HO minus. We do OH for that. But I mean, that's the general rule, though. Like I said, what is chemistry unless we have a few exceptions to the rule to keep you studying harder? So when we write them, this is again, we put the more metallic ones on the left. So nitrogen is further to the left than oxygen, so it goes first. And sulfur is further down, so sulfur goes first. And then this is relative to oxygen, so that's the way we pick it. So the further to the left, further left, further down. So we also have polyatomic ions. So we have monatomic ions. So if you're in a monogamous relationship, you are with one person. If you are in a polygamous relationship, you are with two or more people. So that's polyamory. And so polyatomic ions means two or more atoms in the ion. An ion, of course, is something that holds a charge. And when we have a polyatomic ion, we group them together with parentheses to show that there's that many groups of things. So, for instance, here, so NO3 minus, this is known as the nitrate anion. And the nitrate anion means that this one nitrogen and three oxygens as a group carries a -1 charge. And the formula unit for magnesium nitrate is magnesium parentheses NO3 2. So that means there's 2 units of NO3, 2 units of nitrate in this molecular formula. So looking at this, this is pretty much what I said, and then same idea. So we can have 3 different types of chemical formulas. Empirical formulas is a simple whole number ratio of the atoms of each element. So most formulas are empirical formula. So I mean, they're one and the same. I mean, there are quite a few exceptions, but they're more or less, most formulas, the empirical formula is the same thing as a molecular formula. So the molecular formula is the actual number of atoms in the compound. So if you look at hydrogen peroxide, for instance, H2O2, the empirical formula, the simplest ratio is 1 hydrogen and 1 oxygen. There are different elements that have several of them. So for instance, carbon and hydrogen can have the formula CH. So acetylene C2H2 has the empirical formula CH, and benzene C6H6 that also has the 1 carbon and 1 hydrogen ratio, but those are 2 very different molecules. So empirical formulas are not always the same thing as molecular formulas, and even though 2 molecules have the same empirical formula, they can have vastly different properties. In a structural formula, this uses lines or kind of groups to indicate what the shape of the molecules are. And these are all models. You can use molecular models and space-filling models and ball and stick models. These shows you the connectivity of the molecule, so you know. And this is important because it tells you what kind of functional groups there are in there. So for instance, the formula for ethyl alcohol and dimethyl ether, those are both organic carbon-containing compounds. They are 2 different compounds, and they have 2 different sets of properties, even though they have the same number of atoms, but they have different connectivity. So that's one thing that's important, that the structural formulas are very frequently listed for certain molecules like that. So here is the molecular formula, CH4 for methane. Structural formula, this is also known as a Lewis diagram. And then the ball stick model and space filling model. So very frequently you will see all 3 of these. More commonly, you'll see the structural formulas, and you can easily look these up in certain things like Wikipedia, for instance, if you're looking up molecules. So the general idea of the color scheme follows this on the right. If you are colorblind, it's usually you can look at the Lewis structures and then kind of figure out. I mean, you can if you understand the way the atoms go in space, you can tell the difference there if the colors don't make sense, and hopefully the size can also help you in discerning them. So with methane, the molecular formula shows that there are 1 carbon atoms and 4 hydrogen atoms. And then the structural formula shows that the carbon and the hydrogen are attached to each other. Both the ball and stick and space filling model, you can see that it follows a tetrahedral sort of geometry. So for me, I can go in between the structural formula, the Lewis diagram, and the ball and stick model and space filling model in my head. But as you get more experienced in this, you can be able to do that. So with molecules, we can see both the macroscopic can show the connection between the macroscopic world, the big world, and the atomic molecular world. So we see things like H2O, and then then next to it will have L. So this is coming in the future. H2L state L, that means liquid water. And that is exactly what this is shown right here. And you can see, like, although you can't see molecules this size because they're too tiny with light, but it's a model, it's a representation. It's one way that we chemists can describe the world using our models. And remember, pure substances can be either elements or compounds, and elements can be atomic or molecular. Well, I mean, although the textbook doesn't go into too much atomic, they consider metals to be atomic solids. I consider them to be a different sort of bonding. I consider them to be metallic bonds. I think there's a difference between iron metal bonding and carbon diamond bonding, for instance, but I'm kind of going beyond the scope of this textbook here. Compounds can either be molecular or ionic. Molecular means sharing of electrons. Ionic means that one group, typically a metal, gives electrons to another group. So to show you here, pure substances can be elements, or they can be either atomic or molecular. So showing there, neon gas is an atomic part, molecular, like diatomic oxygen. Compounds can also be molecular ionic, so water is an example of a molecule. Sodium chloride is an example of an ionic compound. And also showing here acids. We're going to talk about acids in a little bit, but for binary acids, and we will go more in depth in the way we describe acids as well later in the chapter, but for two elements that have, so you say hydro, base name of the nonmetal, plus ic plus acid. So for HCl, for hydrogen and chlorine, we call it hydrochloric acid. For oxy acids, the ones that contain oxygen, there are a lot of those. So if the polyatomic ion ends in ate, we call it ic acid, and if it ends at the polyatomic ion ends in ite, and we call it an acid. So for sulfate, we call it sulfuric acid. For sulfite, we call it sulfurous acid. So atomic elements, we have them as their basic units. So I would give it a special classification as a metal for mercury, but sure, we'll go with what the book says. They are not necessarily single mercury atoms. They're kind of more like electrons flowing between them. There is a sharing of electrons alongside these elements, and that's the reason why they can conduct electricity, for instance. So they tend not to exist, molecular elements. There are a few exceptions. I mean, certainly, our atmosphere is 98% or more of oxygen and nitrogen, which are molecular elements. But that's kind of the exception, the rule, than the general rule itself. Like I said, what's chemistry class unless we contradict ourselves a few hundred times, right? So, but other elements like chlorine, it tends not to exist in nature as diatomic chlorine. So here are some elements that are diatomic molecules. You can see the simple nonmetals, all the halogens and oxygen, nitrogen, and hydrogen, for instance. And diatomic, so that means di means two, so diatomic means two atom molecules. And a molecular compound, we have two or more nonmetals. So carbon dioxide, for instance, this has the two nonmetals of carbon and oxygen, of course, in a ratio of 1 carbon to 2 oxygens. And for instance, dry ice, if you've played with it, this is solid carbon dioxide. So, and going on, talking about ionic compounds, metals generally tend to lose electrons with nonmetals. And in this case, the bonding is called ionic, because the bonding has to deal with the Coulombic force, meaning the like attracts, or the like repel and the unlike attract, and then it forms a crystal structure, and then the combination of the attraction and the repulsion gives its structure. And also ionic compounds tend to be brittle, and many rocks, for instance, are ionic compounds. You can see you can hit a hammer on a rock and they'll shatter, kind of thing. So that's what I mean by brittle. They tend to shatter, and versus metals that tend to be more ductile or bendy. You can smack a metal with a hammer and you get a dent in the metal. It doesn't shatter the metal. So this shows you here the sodium chloride. And if you think about this, if you see a three-dimensional array, if you smack this hard enough with a hammer, if you move the chlorine atoms next to each other, it causes repulsion, which will cause the crystal to break. So that's why you can pound salt, and you can pound salt to very fine things because of the nature of the bonding there. And ionic compounds, it says generally when metal goes to non-metal, you can have ionic compounds with all non-metals. So a fertilizer, ammonium nitrate, for instance, that's all non-metals, but there are also polyatomic ions that do that. But for each molecular unit, and especially here for the ionic compounds, the charges have to be electrically neutral. So for instance, NaCl, sodium is a +1 ion and chlorine is a -1 ion. So we have to have a 1-to-1 ratio there to make sure it has a zero charge. And so let's try and determine then the ratio of elements in magnesium chloride. So magnesium ion, it's an alkaline earth that tends to form +2 charges, and chlorine is a halogen. It tends to form -1 compounds. So since magnesium has a +2 charge and chlorine will form a -1 charge, we need twice as much chlorine atoms to equal out the +2 charge of magnesium, thus giving it the formula MgCl2 for 2 chlorines to 1 magnesium. So how do we figure this out? You write the symbol for the metal and it's charged, followed by the symbol of the non-metal for its charge. Make the magnitude of the charge on each ion become the subscript for the other ion, and then see if the scripts can reduce to the ratio of smallest whole numbers, and then go and check to make sure the sum equals 0. You can also look at this by finding the least common denominator. So if you remember doing fractions, and this is the same way that you find the least common denominator on a fraction mathematically. So for instance, aluminum and oxygen, aluminum tends to form a +3 ion, oxygen tends to form a -2 ion, so you switch them back and forth, and both 2 and 3 are prime numbers, so we can't divide them. So we know that we're probably good there, but let's go ahead and double check. So for aluminum, 2 times +3 is +6, and for oxygen, 3 times -2 is -6. So both of those have balanced out, and this is a proper formula. So same thing for magnesium here. You can follow the same procedure and then get 2 parts magnesium and 2 parts oxygen, but you have a common denominator of 2, so you can divide it down to just magnesium, oxygen, like 1 magnesium, 1 oxygen for magnesium oxide. So it's what's the least common denominator of 2 and 2, and well, I mean, it is 2, but I mean, then they divide out to go for 1. So here are some groups of polyatomic ions. I hate to say this, but it might be easiest if you just memorize these. And I'm going to say the names so you can be familiar with the names. Acetate, carbonate, hydrogen carbonate, but more frequently we use the word bicarbonate. When you say the word bi in chemistry class, it usually means extra hydrogen. So it is carbonate. Bicarbonate is carbonate with an extra hydrogen, so bicarbonate. Hydroxide and nitrate and nitrite. Also, next one is chromate, dichromate, phosphate, hydrogen phosphate, also known as biphosphate, ammonium hypochlorite, chlorite, chlorate, perchlorate, permanganate, sulfate, sulfite. Oh, we have a repeat of this. Did I miss one? Oh, wait, I went up. Sorry. Sorry, folks. Hydrogen sulfate or bisulfate. I'm sorry, hydrogen sulfite, sorry. Hydrogen sulfide or bisulfite, hydrogen sulfate or bisulfate, peroxide, cyanide. So when you do this, so what do we do about polyatomic ions? Same idea. Each polyatomic ion has a charge. How we were doing with just monatomic ions before, we do the same procedure for the polyatomic ions, and you balance the charge. So between calcium and nitrate, for instance, nitrate is a -1. I don't know why it has a 3 on this. It must be a typo. It's a nitrate is a -1 polyatomic ion, and and calcium is +2. That means you need 2 nitrates to overcome the +2 charge in the calcium. And there are some general things with metals and nonmetals. Generally speaking, for instance, the alkalis tend to be +1, the alkaline earths tend to be +2. But they're in the transition elements, so that's the middle of the periodic table, they can oftentimes have variable charges. This is not always true. Some have consistent charges like zinc and silver, but iron, for instance, can be +2 or +3. So we have to be more careful about this, and they're both very common. So it's easiest with this, well, the metal that forms only one type of ion, but we have to be a little more careful about the metals that form more than one type of ion. And for binary compounds, and these are ionic compounds, we use the name of the metal as the cation, and then the base name of the nonmetal plus IDE. So we use this to describe the names for this. So generally speaking, the main group elements, that's the first 2 in the last 6 columns of the periodic table. These tend to have single charges. There's a few exceptions. Tin and lead. Sn is tin and lead is Pb. We have to use the variable part of naming for those ions. So name the compound. NaCl, we use the name of the cation, which is the metal sodium. Even though it's a sodium +1, we still call it sodium. And chlorine is going to be the anion, so we call it chloride, sodium chloride. Same thing with aluminum and oxygen. So we're going to say aluminum for the name of the cation, then oxide for the cation. And since these have typical ratios, we don't have to discern between them. So here are the elements that tend to have one charge. So, and these are the names. I'm going to go ahead and say them. So the metal, or the non-metal element, fluorine, anion name, fluoride, chlorine, chloride, bromine, bromide, iodine, iodide, oxygen, oxide, sulfur, sulfide, nitrogen, nitride. So the type 2, and that just means the ones with variable charge, we have variable charges in the periodic table. This is not always true, right? So zinc, silver, and scandium, for instance, have set charges typically, but we have other types for other elements. So for these ones, the older name, no one really uses that. The chemist is going to be neck high in his or her grave if the chemist is using the older name. It's not typically used. The newer convention holds much more frequently for this. So, but we're just kind of showing it because we've talked about history and other parts of this class. Why not improve it with why not include it with the nomenclature? So here's some more of that. But you might notice some of the Latin names. So stannum for tin, and plumbum for mercury, right? And that's also where the word plumbing comes from, by the way, because pipes used to be made of lead. So because of the variable charge, we have to include the charge in the name. So, and we do this not with necessarily Arabic numerals, we use Roman numerals. So with copper plus and 1 and copper plus 2, we use the word copper 1 and copper 2 in the name. So that means that for variable charge ionic compounds, use the name of the metal, then the charge in Roman numerals. But when you say it, even though it has the Roman numerals, you say it using the name. So you don't say iron III chloride, you say iron 3 chloride, but you write it as 3 in Roman numerals. So let's determine then the charge of the iron and iron 3 chloride. I just gave you the answer. But you have to look to see if you need iron. Iron tends to be +2 or +3. Chlorine, though, is pretty set at -1. And remember, units have to be electrically neutral. So for the chlorine to be 3, that means there's a -3 charge. That means the iron has to be +3 to make it neutral. So that's how you can determine the charges of the other elements in these molecules, even though they are variable. And when we call it iron 3 chloride. We write it as iron parentheses III close parentheses chloride because of the convention for Roman numerals, but when we say it, we say iron 3 chloride. So hopefully this is making sense for you guys. I know it's complicated. And some compounds also contain polyatomic ions, so they use the same procedure, but we use the name as the polyatomic ion whenever it occurs. So for instance here, KNO3, this is known as potassium nitrate. So you use the cation name potassium, it's just the metal name, and then nitrate is the name of the polyatomic ion. Now iron 2 hydroxide, so hydroxide, from if you look at the chart and see OH minus has a -1 charge, that means there's 2 units of -1, so that means that the iron is forced to be +2. So we name this iron 2 hydroxide, and 2 in Roman numerals in the written part. So if there's 2 polyatomic ions, we just use the name of both polyatomic ions. Ammonium nitrate, for instance, here, and this is this is an ionic bonding, but there's no metals in it. I mean, there's others. They're fairly, I don't want to say they're rare. Ammonium nitrate is very commonly used. It's rare in terms of number, but you can have ammonium phosphate, for instance. So that's another one that you can go. That's all nonmetals. So many polyatomic ions are oxyanions, and unfortunately, there's no convention, but one of them got the ATE, so and the number is not consistent, unfortunately, but if it has 1 less than the ATE end, it's ite. So sulfate, so the sulfate is SO4, and that means the sulfite has got to have 1 less oxygen. Same thing with nitrate. Nitrite has 1 less oxygen. So if you have hypo means 1 less than the ite, and then per means more than usual. So let's look here at that chlorate. You start with chlorate. 1 less oxygen is chlorite, and 1 less is hypochlorite. But then chlorate 1 more is perchlorate. So same thing, starting with bromate, 1 extra is perbromate, 1 less is bromite, 1 less is hypobromite. Iodate, 1 more, periodate, 1 less than the iodate is iodite, 1 less than iodite is hypoiodite. So you can see this is getting more and more complicated. But we have a set procedure, of course. The only problem is what the 8 ion is not held consistent. So for instance, bleach is sodium hypochlorite, and I use this quite a bit. I use it for cleaning. It's good for laundry and for cleaning things. Baking soda is the bicarbonate of soda, and soda is sodium carbonate. So sodium bicarbonate. That is, we use this. I use it to brush my teeth alongside toothpaste. I mean, it's got many uses. We use sodium bicarbonate in our bodies to as a buffer as well. It keeps the pH of the blood from changing. So calcium carbonate. This is used in antacids, and it also, if it combines with acid, it forms carbon dioxide gas. Sodium nitrite. So this is used in meats. It's used and typically gives the meats kind of a pinkish color, and it's used for keeping bacteria from growing on them. So let's move on to talk about maybe molecular compounds. And so molecular compounds, so these are different than ionic compounds because these are going to have pretty much all nonmetals. It's very rare that you have a molecular compound that's got metals in it. There are exceptions to the rules that have that. So dilithium, for instance, for those of you Star Trek fans, there actually does exist dilithium, but it's very rare. And it won't give you a warp drive, so I hate to break that to you. But there are metal molecular compounds, but generally speaking, nonmetals are the ones that exclusively form nonmetal compounds. So we have the way we name them is we have a prefix that indicates the number and the name of the first element, then the prefix of the name of the base name of the second element plus IDE. So similar to the ionic compounds. And also, if the first element has 1, we typically drop the mono prefix. So here are the numbers. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. And you can think of geometry. So some of these, although we call a rectangle, we don't call it a tetragon. But we have a triangle and a pentagon and a hexagon and octagon, right? So similar. You can see these prefixes used in other situations as well. But that's the ones we use there. And like I said before, we drop mono for the first one if the first element is 1. So let's look at here this compound N2O, dinitrogen monoxide, also known as laughing gas. So when you write this, the same procedure, we start with the first element and we have the prefix. So there's 2 of them. So we say dinitrogen, and oxygen, it's the ox, and then IDE, oxide. So, and there's 1 of them, so we use mono, so dinitrogen monoxide. So we do it that way. So here for CO2, we call it carbon dioxide. We don't say monocarbon dioxide. We drop the mono if the first element is 1. So we drop that 1, so it's just good old carbon dioxide. For acids, when it's hydrogen, we first write in the formula, and so we have to identify the compound as a acid. For hydrogen, it's usually written first in the formula, and then it's written second. For more nonmetals, it's written second. So the second rule is more for organic chemistry, which you have to. It's going to be much further along. But what are acids? Acids, the hydrogen tends to pop off, and when it forms in water, and then the acids tend to add positive charge to things, and bases on the other way tends to add negative charge. So that's one thing with acids. And for this class, of course, it's much more complicated. Although this is for use in most like household and industrial uses, this does hold true. Binary acids means there's only hydrogen and a nonmetal. And then there's oxyacids that have hydrogen, a nonmetal, and oxygen. So there are more than that. So you might hear the term fatty acids, for instance, but that's for organic chemistry and biochemistry, which you can take in a different class. So I have a horrible habit of telling you guys the absolute truth because I don't want to try and dumb things down for you. I want you to understand that there are other classes and other applications for this coming up. So I hope I'm not running circles around you guys. But I mean, why would you listen to this video if you can just read the textbook? You know, you get some little extra information here. So acids that have the H as the first element, binary is only 2 elements. Then the other ones have oxygen. So it's a little different when you get to organic chemistry, though. So naming binary acid, you have the hydro base name of the nonmetal plus ic acid. So like for HCl, it's hydrochloric acid. And so here it is, hydrochloric acid. And you see the state there, and AQ. That means aqueous or aqueous, depends on how you want to pronounce it. Aqueous and aqueous are both correct. It means dissolved in water. So, and then we have HCl. We would have to call this hydrogen chloride because it's in the gas phase. So same idea with HBr. This is hyperobomic acid in water. And then H2S, this would be hydrosulfuric acid. And you usually see this in the gas. It's H2S gas, and it smells like rotten eggs. It stuff smells horrible, absolutely horrible. In humans, we can smell sulfur in the -2 oxidation state like it is in hydrogen sulfide down in the parts per trillion, and we don't like it. So that's one thing about this stuff. I can see this molecule, I can smell it. So oxyacids, and there's a convention for this. So you see the same thing with the polyatomic ions, and now we need to name them. So naming them is a little more complicated, and it depends. The number of the hydrogen ions depends on the charge of the anion. It's the oxyanion. So the formula has to be charged neutral when it's together. So for oxyacids that contain hydrogen, the oxyacid that has oxygen, the ite, the oxyanion ends in ite, and the ate, the oxyanion ends in ate. So then we have to use the base name of the oxyanion plus us acid. So I'm sorry, the names of the oxyanions that has ite, we change it to us and then acid. And well, then the charge is already there. And if it's 8, we call it ic. So the 8 forms the ic. So I'm going to go ahead and say these. So HNO2, the oxyanion name is nitrite, so it's nitrous. So then for the oxyanion nitrate, it's nitric acid. For sulfite, it's sulfurous acid. For sulfate, sulfuric acid. For chlorite, it's chlorous acid. Chlorate, chloric acid. Acetate, acetic acid. Carbonate, carbonic acid. And then this here is the overall summary of the nomenclature flowchart. If you are allowed to have a crib sheet, this is something you might want to put on that crib sheet or keep this handy as you're doing your work. So you can use the flowchart. So CO, it's molecular. We're going to call it carbon monoxide. Next one down, calcium fluoride. It's ionic. I know I can just look at it and I can say it. It's an ionic compound because it has a metal and a non-metal, and it has one type of ion. So HF, aqueous, since it's in water, it's an acid. So it's then for fluorine, it's fluor, and then plus the ic. So hydrofluoric acid, nasty stuff. So FeNO3, So this is an ionic. It has more than one type of ion. Nitrate tends to be, is -1. So 3 -1s means the iron is +3. So we say iron 3 nitrate. And then, it has the H first, so it's an acid. And then it's an oxyacid, and it's an ATE. So ClO4 is perchlorate. So this is perchloric acid. And same thing here, it's an oxyacid, and SO3 is sulfite, so we call it sulfurous acid. And you could follow the chart on the previous page to know this. So let's talk about formula masses then. Formula masses, and this is one where you just have to count the number of atoms and use the atomic mass. And the atomic mass is the bottom number on the periodic table when you look at it. So, and you sum this up for each of the elements in the molecule. So it's just the number of atoms that have of one element times the atomic mass, plus then the number of atoms in the second element times the atomic mass of that element, and so on until you've covered all the elements. So for magnesium chloride, the formula mass, the magnesium's atomic mass, look at the bottom number of the periodic table, is 24.31 atomic mass units, and for chlorine it's 35.45. But there's two of them, so you have to multiply 35.45 times 2, and you sum that together and you get 97.21 atomic mass units for the formula mass of magnesium chloride. So here's a review, and much of here is going on, a lot of action in this chapter. So compounds have consistent composition, at least as far as the ratio of the elements. Chemical formulas, we can use them to describe various things, the ratio of the elements, and we can go further and give molecular compounds. Chemical nomenclature, we talked quite a bit about naming, and we ended with formula mass just very briefly. Now that you know how to name things, you can see how figuring out the number of each of the elements, multiply it by the atomic masses, which are found in the bottom number of the periodic table for each element, and then that tells you the formula mass of the entire compound. And that's going to be important when we talk about moles. Here are the learning objectives and the legal. Thank you for listening.